Please welcome Dave Rumsey to open this Digital Humanities conference.
Thank you, Mike. I'm quite excited about my collection coming here to Stanford. I know we're going to have a lot of fun with it. And I'm also excited that Salim is here tonight. Good to see you, who will be shepherding the collection. And thank you for having me here this evening to give my talk, which will be about reading historical maps digitally, how spatial technologies can enable close, distant, and dynamic interpretations. But first, let me say, as I looked over the 400-plus pages of abstracts, quite a book, for this conference, I was pleased to see that your Big Tent digital humanities fields involve so much spatial and visual thinking. I used one of your tools. I did a simple text analysis of all the talk abstracts, not my usual activity, but it was so interesting to see the many uses of words relating to space, place, mapping, visualization, and graphing. As many words, really, as were used for digital and humanities. So I felt more at home coming here, given my lifelong obsession, as Mike has detailed, with maps and space. As digital humanities evolves, I think the old barriers separating text and image will begin to blur, which I think will be a good thing. Maps combine text and image as part of their essential structure. For example, this 1846 map of the mountains and rivers of the world done by S. Augustus Mitchell is quite extraordinary. It shows the highest mountains here all piled up on top of each other and the longest rivers hanging down like snakes. In a visualization that's really remarkable for its simplicity and clarity. It includes text along the sides, and just at one view says a whole lot about major parts of the world's topography. Because of this dual text-image aspects, maps really challenge us, I think, to understand them. Here are details from about 20 maps that show the many ways that maps work at visualizations. Maps are dense, complex information systems arranged spatially. While they share similarities with other visual artifacts, their uniqueness as spatially arranged visual information requires special digital approaches, I think, to understand and reuse their content. Geo-Referencing, vectorization, virtual reality, image database, and GIS-related tools all work to unite our eyes, minds, and computers in new ways that can make historical maps more valuable and accessible to humanists concerned with place and space over time. In this talk, I'll explore the tools and techniques that I use to work with maps that also may have implications for the ways digital humanists work with visual information generally. Using imaging technologies to help us unlock the information in historical maps is a big challenge because maps operate at multiple levels of meaning, from picturing so-called real space to visualization of natural and human data, historical events, cultural information like land ownership, political boundaries, conflicts, and much more. Maps incorporate elements of art through culture, science through measurement, and history through time. A map is a kind of proto-image and a super-narrative. It communicates both above and below the narrow bands of language and observation. Because maps are created as visualizations of information themselves, it's especially challenging to create additional digital visualizations of the maps. It's a bit like making a visualization on top of a visualization. So it may be helpful, I think, to use an idea from your world, the idea of readings, both of image and text, as an approach to sorting through the various ways that digital technologies can allow us to make close, distant, and dynamic readings through image databases, interface design, georeferencing, and GIS tools. Let's look at an overview of the various ways that this happens in my work. Here is a marvelous map of the Mississippi River from 1858 by Norman, published by Persac. It's one of the great antebellum maps that shows all of the land ownership patterns after the French along the river, with high resolution imagery, which is sort of the cornerstone of close reading of maps. We can zoom in and see this map in huge detail digitally. This is in the Luna database, which Mike mentioned. When the same map is geo-referenced, that is brought into GIS, now we have the ability to compare it with other information layers. Here, the satellite view, the same part of the river, and also then to look at it obliquely and combine it with other data. Distant reading in an image database is enabled through viewing hundreds of thumbnails at once. Here in the Luna database, dynamic reading and distant reading in GIS happens when we join hundreds of maps together, as this project we're doing now of the German National Survey. Dynamic reading happens in virtual worlds, and virtual globes can be rendered in GIS. We can literally read a book with digital page turners. Tunnels of thumbnails in virtual worlds create 3D browsing. That's Mr. Darwin that Mike mentioned. And at the other end, we have serendipitous viewing with random thumbnails, globes, maps in globes, and here overlays of many maps at once. We have interface design is increasingly important as well, though. So here we have a new search by map interface that I've just launched that I will discuss. Also, we have an older interface that shows how you can search 4 maps at once, and then layerings of many kinds of information. Here, overlaying modern buildings with historical maps. And finally, vectorization, which is our latest project and our most difficult, actually, where we extract information to put into databases directly from the maps. Here, the Norman Persac map that I showed earlier. These various techniques enable multiple readings of the maps. So we can do many things with these tools. But first, let's take a look back at how scholars like yourselves worked with maps long ago. And what kind of tools did they use? Well, one of the most interesting is the printed facsimile that was made by A.E. Nordenskiöld at the end of the 19th century. He published a facsimile atlas which included a wide range of reproductions of maps from the 15th and 16th century using photolithography. Maps ranging from Ptolemy to the Lefreri atlases to Mercator and Ortelius and Whitfleet. The reproductions make this an important work. They're not just illustrations to the text, but rather occupy full pages, in many cases full-size facsimiles, including the complete 1490 Rome Ptolemy, the world map of which is shown here in 27 sheets, with a remarkable composite image that shows all 27 sheets overlaid on the Ptolemy world map. This was very forward-looking and relates to a lot of the things that I'll show you. Then the Ulm Ptolemy of 1482, the Silvani Ptolemy of 1511, the Mercator world map of 1538, the Ortelius of 1570, and the Halkett from 1599. For the 1597 Whitfleet, there's a full page of composites showing North and South America assembled together. Again, very forward-looking. But this copy of the Nordenskiöld that's in my library is special for another reason. It was the personal copy of Henry Stevens. Mr. Stevens was a very prominent early 20th century map dealer, second generation, worked in London. And this copy has, as you can see here, Stevens' extensive manuscript notes as he compares 5 copies of the Lefreri Atlas. Here are the copies with the abbreviations he's made for them. And here are his notes. So So he's doing something that we routinely do now digitally, but we can see how he worked it through over 100 years ago. He made drawings along with his notes. He made visualizations of the maps, how they differed, sort of visual annotations, even with the cartouches themselves. His small thumbnails of these map cartouches remind us of comparative works with digital thumbnails today. For many decades, this kind of photographic reproduction of the maps assisted analysis and dissemination, primarily in monographs and journal articles, but also as individual facsimiles. This method of republishing did not change the fundamental way the maps were read. With readers' eyes and minds, the maps were explored for their information, probing rich layers of data that the maps contained with their use of symbol, scale, font, color, dense graphic representation of information. But while this method expanded access to historical maps, it was still very limited compared to the near universal access that the internet has enabled in the last decade. If Stevens were alive today, I fancy that he would know how to use our new tools. He probably would have set up something like this on my site, a group of atlases by the American publisher Joseph Colton, 7 atlases from 1856 to 1886, with all pages and thumbnails for comparison, as you can see here, and also the ability to compare enlarged images, such as these showing changes in the Dakota Territory from 1857 to 1886, here enlarged to show the changes in the mapping of Lake Minnewacan, or Devil's Lake, over 30 years. Stevens and Nordenskjöld anticipated the power of image collections for mining the data, I think, in historical maps. Until recently, it's been primarily specialists in the history of cartography and map making that have been the primary users of both original historical maps and facsimiles like Nordenskjöld, because the barrier to entry was extremely high. The maps were scattered over many collections in many libraries in many countries. With the advent of the internet and advanced digital imaging technologies starting about 15 years ago, access now to tens of thousands of historical maps is possible through online map libraries, and gradually humanists in and outside the academy have been using historical maps in teaching, research, monographs, and articles, going well beyond the history of cartography into other areas of research. Over an 11-year period, we've seen requests for reproductions from my own online library go from about 1 a week to now more than 5 or 10 a day. Examples range from French environmental historians using this 24 gigabyte composite image of 18th century Cassini survey in France to measure the forest cover at the time, which is represented here by symbols on that map. Another example is Indian tribes in the U.S. using the many references we have in our General Land Office maps from the late 1870s and 80s showing the then very large Indian reservations to visually show the history of frequently broken U.S. treaty commitments. To Bethany Novisky's wonderful article on Francis Henshaw's map primer, which helped us to actually significantly improve our metadata based on Bethany's research. To experiments in computer reading of our maps by the hundreds being done by Peter Baichi and colleagues at the University of Illinois. With the growing interest and use of these historical maps, my responsibilities as an online digital librarian grow each year. My challenge is to increase access and to improve tools for analysis, understanding, and reading of the maps. We'll take a closer look at the various technologies I use and the readings made possible by them. Database and interface design for large map image libraries allows expanded access to many, many historical maps. These digital libraries are complex interactions of image compression, database visualization tools, faceted browsing, and more. Image libraries like my own, as you can see here, give the ability to view hundreds of maps quickly through visual browsing. We can quickly assemble groups of maps. Here, maps of North America arranged by date from 1756 to 1777. We can represent entire atlases, such as Henry Popple's Atlas of America from 1745, here with all the pages as separate images, and then as one giant composite image that allows us to zoom in through multiple levels of scale, a whole new way of seeing the maps and the book. As well, we've now added book readers to my site, where we can look at the book not just as information, but as an object in itself. See the versos of the pages, turn the pages, see how one page leads from another. We host this through the Internet Archive, but have incorporated it into the Luna browser. This, I think, is going to be increasingly important, these kinds of book turners, as we incorporate more and more atlases into our collections. We can also zoom in. We can do everything that we do with individual maps within the book. And on the left side, we have all the thumbnails of the book. So you can browse through and get a sense of the whole thing quickly as a group of pages, and then select any individual page and go immediately to it. We have just recently added to the site, after working for over a year with Peter Priedal in Switzerland, who's a wonderful programmer, this search by map. And as you see, you have a Google map, and it's set to San Francisco with the results set on the right. You can click on any map that results, go into the Luna database, do the normal activities, panning and zooming, looking at metadata. What is great about this is it's very fluid. As you zoom out, all the results change on the right. They follow the coverage of the Google map that you're looking at. So it's a very fluid way. As we pan, we see maps of Central California. Then we zoom out, it changes to the state maps. All the maps, of course, in the database have to have coverage information. It's the MARC 034 field that we provide. We have about 12,000 maps out of the entire 27,000 online done, and we'll do the rest, we hope, over the summer. We can change scales, limit scales to 1 to 500,000, and then we can see groups of maps with smaller coverage within the same area. You can also put in other limiters, like in this case Wheeler, keyword, and it brings up the Wheeler survey maps that fall within that window. This to me is a wonderful way to browse through and find content in the collection without ever entering the keyword, but just really looking at coverage. As we pan around and move out to America, we see maps of America. We pan out further to North America, and we get maps of the North American content. We have a timeline. You can limit your results by date. And there's also a find a place location that you can use. So we're very excited about this kind of tool. Again, it facilitates a kind of use of a large database. Discovery is very important in all these digital libraries. At the other end of the spectrum, we've long had something called the ticker. This has been up on my site for over 6 or 7 years. It's a random look at the whole collection in about 8 hours, exactly the opposite kind of experience. The maps float by. It feeds on serendipity, really. You find something that you're interested in. You get brief metadata. And then when you decide that there's a particular map that you want to look at, for example, like this map of Alaska, you click on it and it goes into the Luna database, and you can do the usual Luna operations. For those who really want to get obsessed with this tool, we will allow you no end of browsing. You can put up 5 or even 10 of these at once. And of course, that shortens the time it takes to see the whole collection, but it takes a little more looking. So this is a serendipity tool, really. So tools like this make possible extensive use of historical maps, and they open up the process of working with them. They allow distant readings of hundreds of maps at once through browsing, comparison, and searching, something that really is almost impossible in the physical library, along with the close reading of maps through zooming and panning that reveal details that would be very difficult to see in the original. and the ability, as I said, to create large composite images from maps that were published separately but intended to be joined. Using GIS tools with historical maps, of course, begins with georeferencing, the originals. Here's the original map. Here it is georeferenced now in Google Earth. Georeferencing allows us to combine the map with many other kinds of information to overlay the map on top of satellite images, shapefiles, see changes over time. And when, as I'll show later, when there are maps as part of a series, it allows the creation of these huge carpets of maps at once. Here we look at San Francisco, 1859, by the Coast Survey, look at Mission Bay, see how it was filled in over a century. We can also look at it obliquely and turn on the 3D layer in Google Earth of the modern built city and see how that relates. A whole other kind of reading, adding the highways, looking at the tidal basins near Yerba Buena. We can see how much of the south of Market and impending Mission Bay development's been built on very shaky ground. We can also use digital elevation models here with the Wheeler map from 1883. The original map shows elevation through hachsuring, a wonderful 19th century technique. When we georeference it and combine it with a modern digital elevation model, in this little animation, we can stretch the map and now see it in 3 dimensions. Going in the opposite direction with San Francisco Bay from 1925, we can use a bathymetric model. Here, we combine the bathymetric model with the San Francisco chart. Now we can see what we call its tin structure, which shows a whole new way of looking at this chart. When maps are georeferenced, they can also be put in our quad viewer, which allows looking at 4 maps, all different sizes, at the same scale, moving together, panning, zooming. As I said, large composite maps are a powerful use of GIS. I'll show 3 examples. The Cassini survey of France first, 182 sheets. The first really accurate survey of a country, all sheets done on the same scale. This is Paris, sheet number 1, of course. Here they are all joined. This is a 24 gigabyte image. Now we can see large parts of the country at different scales, something impossible with the originals. Moving in to look at the forest cover that I mentioned earlier. And here it is in Google Earth. Another example is Philippe van der Meulen's marvelous 1827 Atlas of the World in 400 sheets, all on the same scale, the first lithographic atlas of the world, published in Brussels. We've done 2 continents so far. Here they are. They're all in the Luna database, but now we've georeferenced them. They're in a conic projection. You can see how they slant up. They're intended to be joined. He meant to build a globe, and he did actually in 1830, about a 30-foot diameter globe with all the sheets. So we recreate this. We've done South America as well. And then we have put them into a virtual globe. So van der Meulen's atlas read by itself is extremely difficult to read because the sheets are all really disconnected from each other. In this kind of assembly and reading, you can now get a sense of his real purpose, what he intended to do, to put them all together and to show them as a globe. He also sold, interestingly enough, for 10 centimes blank sheets to use to fill in the oceans. I have yet to find those as a collector, but I'm still looking. In addition to this work with van der Meulen, we're currently working on this huge and I think important Carte des Deutschlandreichs. It's a survey of Germany from the 1880s and 1890s. After German unification in the 1870s, they decided they needed a national survey. These maps are extraordinarily detailed. We scanned them at 800 pixels per inch. The eventual composite, part of which you see in the upper left here, will be 300,000 pixels by 300,000 pixels. The physical dimensions of the join map would be 35 feet by 35 feet. Here's the preliminary composite, just 326 sheets. Again, like the Cassini, as you zoom in, multiple levels of scale, marvelous cultural information in this map before the wars, going into Berlin. Here it is in Google Earth. And as good librarians, we also have a complete index in KML on top of it so that you can find any sheet, see what it is, download it, and so on. Here's a look at just a flyover of the Elbe River in Germany, flowing north here to Hamburg. And as we move over it, you get a sense of just the richness of information and the ability to join all these maps and to look at them as one really is a transcending thing with this kind of resource, I think. We're going by Hamburg. We can see the density of the urban town. And then as we move, you see the railroads that are coming in, the beginning of tidal action indicated on the map as we move to the estuary where it opens out into the sea. Just to look at the quality of the survey that they did was extraordinary. We had to find a special datum that I had to invent, but once we found it, everything in the survey went ka-chunk. Incredibly accurate across all 674 sheets, just looking slowly at the modern satellite view. You see the roads align. Of course, there's so many things that are new, but this kind of alignment gives you amazing ability to just do visual studies of this with your eyes, much less what I'll show you in a minute, the vectorization that we intend to do with this as well. Different editions of historical maps, when they're georeferenced, can also be closely compared in a way that is impossible in the physical library. This is John Mellish's 1823 map of the United States, the first map to show the country from coast to coast. Here's his 1816 earlier edition by 7 years. They're both georeferenced. If we go into the upper Missouri River Valley and see the black hills that appear from the long survey on the 1823 Mellish, now as we fade back into the 1816, you can see how they had no idea of this topography. The river has moved incorrectly west in the older version. So this kind of precise overlay is very powerful, very interesting reading that can be done. Digitization of features, either by hand or various automatic vectorizing programs or by combinations of both, enable powerful analysis of maps that have been georeferenced and put into GIS. And they allow combining various shapefiles and other information layers that result into other databases and visualization. It allows us literally to lift data off the map and put it into databases. The Stanford Spatial History Lab, with Zephyr Frank, Richard White has done some impressive work in this process, and they actually encouraged me to move in this direction. Here are some examples of very preliminary work we're doing with automatic vectorizing programs, taking this Bartholomew map of Switzerland from 1922, putting it into R2V, which is a pixel-based vectorizing program. It automatically creates database information on the names, the rivers, the water bodies. Here's the same program applied to the German map series that I mentioned. Incredibly dense information. It picks up all the lines, points, and polygons. Here you can see it a little better if we remove the map. Again, it's very early in this work. There's a huge amount of handwork that has to be done with this, but we're quite excited about it. Another program is called eCognition. This we just started working with. This is, instead of being pixel-based, it's object-based. So this is how it analyzes the map. So I'm very hopeful about this kind of work. What will it mean for us to be able to OCR historical maps the way you do text, the way Mike talked about text mining? It will enable the creation of databases of names, locations of all towns, all buildings, natural features, roads, contour lines, rivers, and more. But it's going to be much harder because the maps are already a complex system. All image overlays each other many times. So we have to teach our computers to read as effectively as our eyes and minds do. But I think the payoff is huge. My feeling it will have more to do with the kind of work that Peter Bakshi's doing, pattern recognition, image recognition. I think it's obvious what humanists would do with this information. It opens up a whole new archive of data that might not exist at all in other places and forms. Then we'll be able to mine this vast trove of data with spatial and temporal aspects and find new patterns of history, both human and natural. For instance, here's the legend for the Carte des Deutschenreich series I mentioned. Just a few of the things that it has. Churches, chapels, monuments, windmills, watermills, factories, brickworks, powder magazines, many other important buildings, 4 different qualities of roads, plus bridle paths, footpaths, railroads, vegetation minutely classified according to separate symbols for broadleaf trees, evergreens, underbrush, heathers, dry meadows, wet meadows, swamps, orchards, gardens, vineyards, and even parks. So you can imagine what environmental historians could do with this. In addition to close and distant reading of historical maps, I think there's something else that I call dynamic reading, for lack of a better word. It includes visualizations that don't neatly fit into other approaches. But generally it means a fluid and changing presentation of maps digitally that combines both close and distant readings. One of our first steps into this direction was the turning 3D map here of Yosemite Valley, which we did 10 years ago. I'm proud to say it still works on our site. It uses a browser plugin and wireframes from GIS. It allows you to see this. This was long before Google Earth existed, but it gave a sense of the three-dimensionality of the object when combined with the digital elevation model. Another thing we've been doing lately is, instead of just two-dimensional overlays of historical maps, here a series of 4 maps of New York City from 1836 up to 1867, we started playing with overlays that are stacked up in space, spatially separated from each other. And getting interesting, it's more of a thinking tool, really, than a research tool, but we're quite interested in it. Another foray we've made is into digital globes. We did this quite a while ago by reprojecting here globe gores from Cassini's 1790 wonderful world globe that he made in Rome. Here, putting it into UTM projection, then unprojected in WGS-84, and then finally putting it in ESRI's ARC globe. This was the first one we made. We were quite excited about it. It can be combined with other digital layers here, the world at night from NASA. Recently, we've been working also with celestial globes. Here, the companion globe done 2 years later by Cassini from 1792. Here it is 64 million meters outside of his terrestrial globe in Google Earth. A whole other kind of view. We started working in virtual worlds about 2 or 3 years ago, initially in Second Life, but we're now going to be moving into OpenSIMs platforms, which I'll say a little about. And that opens up a whole other set of possibilities. Here's we have 4 sims in Second Life. This is my avatar, Map Darwin, flying over the Yosemite Valley map that you saw earlier. We use GIS to bring this into Second Life. The globes are 100 meters tall. Scale is really based on the scale of the avatar here, 2 meters. You can fly inside, see the inside of this globe, where we wrapped the whole GIS around in reverse. In addition, we've been able to use the scale, it's 512 meters by 512 meters, to display very large maps. In this case, this 20-foot scroll of the Tokaido Road that I host for the East Asian Library at Berkeley. It's a marvelous map. It shows the route from Edo to Osaka, done in 1687. Here it is now. In Luna, we have to divide it up. Here, we can, in Second Life, we can lay it out. And it's a bit of a pun, but my avatar walks the road and experiences this map in a whole new way. Another example is this 600 meter tall tower of thumbnails that we built. This was part of my desire after working so many years with flat thumbnail screens in Luna, and it's the art store. It's the common way we look at thumbnails. I wanted to see what it was like to arrange them architecturally and to move through them in 3 dimensions. Again, more of a thinking machine than an actually practical tool, but I've spent hours in here thinking about it, and to me, it points to things. It is done with pretty high-resolution imagery. This is what you see when you put your avatar's nose up to it. It also connects out to our Luna database for high-resolution imagery when you click on any of the thumbnails, metadata, and so on. Certainly, this kind of immersion into the maps at a relatively large scale produces different readings, but I think it's too soon to tell just how useful it will be in the long run. When we have more control through our own open source platform, which is shown here at the very beginning, this just started a week ago, I think we'll be able to get more exciting results. This is my developer, Jason, looking a little forlorn. He's got exactly 2 blocks built. He's got a long way to go. But we will port the entire thing from Second Life to Open Sims. We'll have 16 Sims instead of 4. We will have complete control of avatars, entry, exit, and so on. We can also easily connect to our multiple other databases, which is very exciting. So I think this is a direction we're going into. Going in a completely different direction, going back in time 500 years really. This map I think is interesting as I get to conclude here. It was made 500 years ago and reissued by Antonio Garcia Cubas in his Atlas of Mexico, 1858. It's entitled The Peregrination of the Aztec Tribes. GIS as a tool cannot do much with this map because the map does not operate in real space. Rather, it creates its own spatial system. Yet the map uses GIS concepts of network and timeline as it creates a visualization of a narrative. The travels of the Aztecs over a 350-year period as they moved from their ancient home of Atlan, shown in the upper right, blue square, finally settling in present-day Mexico City, shown by the blue cross in the lower left. Each occurrence of the plant symbols along the footpath marks one Aztec cycle, about 52 years. They began their journey at the end of the 9th century and finished in about 1325. The map shows that spatial concepts and constructions exist independent of the tools we use at any point in time. And as such, I hope that some of the goals and purposes of the readings that I've been showing may have relevance to analysis of other kinds of visual information beyond maps alone. I think the makers of these historical maps long ago certainly would have not envisioned the many new ways that we can reconfigure and reuse them, although I expect that they would approve. New technologies make possible new readings of maps. Close or traditional readings are made even richer. Distant readings, or the ability to analyze the content of many maps at once, are just beginning to be possible and hold much promise in the future as map OCR improves. And combinations of both close and distant readings can create dynamic ways of understanding, exploring, and learning from the maps. For my own work, some of the challenges ahead are in feature and pattern recognition of the maps, the OCR challenge that I mentioned, Open Sims for more control of the virtual space, migrating the GIS to web mapping services, WMS formats that can be used by more people, and getting more involved in crowdsourcing of GIS. I'm hopeful that some of you will have suggestions for us regarding these areas. Now with these historical maps together, we can see the whole Earth represented not only through satellite images, but through historical imagery that reveals how we view our world and our place in the world from earliest times to the present day. Now with our digital tools, we see historical maps as a coherent body of knowledge about the world and its past. Like the millions of texts being read anew digitally that reveal to us otherwise hidden patterns of human thought, historical maps digitally enabled are revealing spatial and temporal context of human activities of generations past and present that we have never before seen. Thank you very much.